Nice, thanks. Right, so thanks for the reminder. Right, so resuming here, question 2 now, which is to continue our review of the material and via the answering some past paper questions. Question 2 deals with a regulated power supply, and we're going to go through the material on power supplies while we solve the particular question at hand. So you're given a regulated power supply here, and the power supply, we have met this configuration before, but there's just one little difference, and we'll get to it in a while. In that there's an extra transistor here, and you all would have known this arrangement from year one. This is something called a Darlington pair, right? And what the Darlington pair does is that if you have a current going in here, the collector, the emitter current out of the TR1 is HFE-IB, and similarly here is HFE, whatever is coming in to the base of TR2. So sometimes they call these things an HFE multiplier. And as an entire unit, because of how it is, you have a common collector, you have an emitter here, the emitter base is in here. So you have a base emitter and a collector. And what happens is that the HFE of this unit is really HFE1, well, TR1 multiplied by HFE of TR2. Okay, so you get a very high current gain. And the usefulness of that approach is that for a very small current going in here, you can drive a large current coming out here, or the other way around. If this particular transistor is being asked to drive a particular current, like in the case of this design, which is on a power supply, so the TR2 is being asked to deliver a particular load current. The drive current that is required from the base of the Darlington pair is the product of the two HFEs less than whatever that current is. In other words, this amplifier here, this op-amp, will not have to provide that much current. Remember, all of these devices are limited into how much current they can source or sink, right? And you look at the spec sheets first. Usually it's a few. In the case of an op-amp, you may be lucky to get up to maybe 100 milliamps, maybe not as high, but usually it's a few milliamps. So to drive a device that is in turn being asked to deliver high current, the Darlington pair is a configuration that is popularly used. All right, and you would have met that before somewhere, but that's the only difference between the type of circuit that we have met, and we'll go through all of them in a minute or two as we cover the material and then answer the question. Okay, so the question asks now, using that to design the regulator to supply a certain voltage and a certain current, and then you're supplying it from a half-wave rectifier, and you're just telling you what type of transformer is a 21 volt transformer, and things like the ripple and so on. The transistors have an HFE. So these are all the things that you need to do. So if you were doing some project, or you want to you're into electronics and you're making a little like a test bench or a little lab bench for yourself, and you say, okay, I need a power supply to deliver some voltage and some current and so on. How do I go about doing it? And that's where this particular what do you call it, question comes from, and the particular material that we're going to look at will originate. So it starts with here. Let me go right back to here very quickly. Right. So there were actually 5 lectures. There was an introductory one on power supply and reviewing rectification and filtering. right? And the rectification and filtering all here. You remember there are two types of, first off, in general, this is what they sort of layout of a power supply, regulated, and we'll come to that term too, of a regulated DC power supply comes in. You have some AC voltage. Typically, this is line voltage, VOLTAGE. Line voltage for most of us is 120 volts, 60 hertz. As I mentioned, if you're in Barbados, it's 50 hertz. And there are some parts of the West Indies, the Caribbean, where instead of 120, you may have 240 volts. Okay? Either way, you're going to take whatever is the line voltage coming in, and you're going to pass it through a transformer, because the regulated power supplies are low voltage, right? Typically, in most situations, for labs and the like, you're probably looking at a VDC max of maybe 15 volts, right? Some cases, maybe 20 volts, usually not more of that. If you're designing some other circuits and so on, internally, you may need higher voltages than that, all right? Okay, so yes, it is recording. All right, so just to make sure here, good. Right, so the main sections are that, and then we saw, okay, well, you have some things about RMS and peak that you know. And in terms of rectification now, there are two types of rectification that are possible: half wave and full wave rectification, right? The half wave, of course, takes the sinusoid in, and when it's rectified, you get only half of the sinusoid surviving. The full wave, of course, gives you that, and then what you get is that at the output, you're going to get for the full wave, the half wave is in red, and the full wave, of course, gives you that, all right? And there are two ways. Well, first off, with the half wave, you only need a single diode. For the half wave, you need a single diode to rectify. And we know the behavior there. The diode will conduct for one cycle and block for the other. All right. And then we know what the average and the average value for the half wave rectified is. Full wave, you have two ways of doing it. One is that if you have a transformer and you have what is known as a center tapped transformer, meaning that the secondary coil has an additional connection in the middle, then with two diodes and a center tap transformer, we can get the full wave rectification being produced. For one half, D1 conducts, and for the other half, D2 conducts. And because of how it's configured, and because of the double secondaries for the transformer, we're able to get the full wave rectification coming out. That's one approach. The other approach is, of course, to use, if you don't have a single, what do you call it, a transformer with a tap, then what you have to use are 4 diodes in a bridge configuration. We call it naturally a bridge rectifier and a bridge rectification. So with 4 diodes now, for the positive cycle, 2 of the diodes conduct, and for the negative cycle, the other 2 conduct. And again, the net result is that you get the full wave rectification coming in. All of them, right, in the case of the full wave rectification, the average DC value is higher, right? And this kind of ties into some of the things we were talking about with the Fourier series this morning too. If you look at this, there's clearly an average value here that is higher. Of course, for the half wave, you're missing this section here, right? So therefore you get voltage, you get nothing, you get voltage, you get nothing, so that the average or DC value is going to be less, okay? And then now, once you get the fluctuating DC, that's only part of the thing. Before you could start using it, right, you have to get rid of some of that fluctuation, and you get rid of it by putting a capacitor at the output of the rectifier circuit. And that now the rectifier, because the rectifier is a voltage or a charge storage device, what it does is that the voltage goes up, and the same time the capacitor will charge, the capacitor will charge up until here. And then when the voltage starts to drop, the capacitor will hold the voltage, and then right until the next time that the voltage changes again. But typically, of course, because there's always some current flowing somewhere, the capacitor voltage doesn't hold nice and horizontal all the time. If it's disconnected and it's a big capacitor, it may well do that. But usually what's going to happen is that the capacitor voltage is going to, let me get my pointer back here. Yeah, very good. The capacitor voltage is going to sag. All right, so it charges up, it sags, it sags, and then when the DC voltage comes back again, it charges up and then it sags. This particular fluctuation here creates what we call a ripple, and we try to reduce that ripple. And remember that the capacitor, if you have a load now, then as the capacitor charges up to here, it's going to discharge through the load. Okay, so the time constant between the load and the value of the capacitor and the load is going to determine how much that sags, and then it charges back up again. A lot of times you have to specify how much ripple you want. The more ripple you want, the smaller the capacitor it could be. The less ripple you want, of course, the bigger the capacitor. In engineering, everything is a trade-off. A big capacitor is expensive, a small capacitor is cheap. So you have to weigh how much ripple you could tolerate as against the price of the component, right? And here's it how for the other configurations for the full wave rectifier, where you put the capacitors. Okay, the capacitors are of course usually electrolytic. ECPROLYTIC, meaning that they polarize. These are the kinds that you see in a can with two leads here. One is positive, one is negative. All right, and you make sure and put it in such a way, if you reverse the polarity, you're going to, the capacitor will overheat and in some cases explode. Right, and while it's fun to have that as an electrical engineering student, it's fun to blow up a capacitor every now and again. It isn't safe and it costs money. Okay, so don't tell anybody I said that. Right, so this is what we were saying, that the capacitor, the voltage flows through the capacitor and it stabilizes it, and we have a certain ripple, right? This, of course, with the time constant for the particular capacitor that you're dealing with will determine how much of a ripple or how much sagging that you have. And we have all the calculations here. All right. Right. The other thing now is that on top of that now is that the thing with diodes is that diodes, when you have a diode and you're putting the diode in a circuit, the diode conducts in one direction but blocks in the other. When it is blocking, it is subject to something called an inverse voltage. All right, so you're asking the diode to hold back a particular voltage. So if I put V plus here and V negative here, it is asking the diode to hold back V plus without breaking down. So the diode all diodes have something called a peak inverse voltage rating, which is how much of a V plus you could put a reverse bias you could put on the diode without destroying it. So when you're designing your particular power supply, of course, one of the things you have to know is what is the peak inverse voltage of the diode, so that the current that the diode is being asked to carry and the peak inverse voltage tells you what size and rating of diode to get. Okay, and as you can see, the various configurations have different different peak inverse voltages. All right, so for instance, the what do you call it? The diode here, when the reverse voltage is just whatever V peak is for this one, but in the case of the full wave rectifier, for this one, the diode has to have, if you look at it, when it's charged to VDC and the voltage is plus VDC in the opposite side, in the opposite direction, like which is like in this area here. You remember this area here, the other side of the signal is being blocked. So the diode has, the capacitor has been putting VDC here on the diode, and then you have VDC being blocked on the other side of it. All right, so the diode, while the cathode of the diode is here, the anode of while the anode of the diode is at minus something, the cathode of the diode is at plus VDC. Right, so you have all of this to consider. So the rating of the diode has to be 2V peak. Okay, you look at it, and there's a similar calculation here. In the case of the bridge rectifier is a little bit better, because what happens is that the diode voltage is, the reverse voltage is split between, like in one direction, is split between two diodes. So in the reverse, so when D1 and D2 are conducting, D3 and D4 are off. So the voltage across them is equally split. So each diode just has to have half of the inverse voltage rating. All right, so it's a little bit safer, but you have, again, the usual trade-off, that you have to create. Here you have one diode, but it has to be a heavier duty diode because it is taking twice the inverse voltage, twice the VS, the secondary voltage. But in the case of the bridge rectifier, you could use smaller diodes, but you have to use 4 of them. So if you're dealing with something where you're making these things by the millions, then you have an issue to deal with. Right? Cost suddenly becomes an issue. And the capacitor, remember the capacitor, if the capacitor is carrying a particular current, then you have to size the capacitor to handle both the current and the ripple voltage. And depending on whether it's half wave or full wave, there's a calculation for the capacitor. So in the case of the half wave, the capacitor is I over delta V by F, assuming that F is 60 Hertz in most cases. In the case of the full wave rectifier, the value is twice, the capacitor is half the value. And you can understand why, right? If I have a voltage going like this, I need a bigger value capacitor to handle what is happening between here than if I have a voltage looking like this, right? The sagging between, there's a shorter period between recharges, so the capacitor here could be a little bit smaller. All right? Right, and these were some examples that we had there. So having the raw circuit, what do you call it, analyzed, then we moved on to, it's the same one here, hold on. After we had that, then we moved on to power supply. Let me get the next lecture here, good. Right. Once we were once we got the basic rectification on the filter capacitor and the diodes out of the way, the next thing is what to do with that ripple. The fact of the matter is that most applications do not tolerate ripples very well. That is what they call an unregulated power supply. There are some applications like I mentioned, like lighting applications, the LED bulbs and so on that you see around, and LED lighting is actually flickering at the line frequency, but you wouldn't notice it. Okay, but it is flickering. And but that particular application, it doesn't matter. But if you're powering something, you're powering a microprocessor, you're powering some device, a lot of times you need a fairly regulated or constant supply. And this is where the regulated power supply comes in. So after you've regulated it, you now have two ways of putting something called a voltage regulator in it. One is called a shunt regulator, and the other one is a series regulator. And then there were some ways that we described it, right? These were just some terms that we use. A basic shunt regulator, a simple way to get a regulated supply for a fairly low amount of current is to put a Zener diode, right? And what is Zener diode? Remember here is your this is from all the either your half wave or your full wave rectifier here. So up until Vin, you have the diodes and capacitors from before. Once you have that now, here is where you have this kind of voltage coming in, right? So something with a ripple. And what you do now is to get something that is fairly stable outside here. You can put something in parallel with the voltage, and one device that does that is the Zener diode, right? Remember what the Zener diode does? It's a diode that is unlike a regular diode, is designed to operate mostly in the reverse bias mode. What it does is that when you reverse bias it, the voltage, of course, it rises until it reaches a particular point, and the Zener diode at that point in time starts to conduct and maintain a very constant voltage across its terminals, called the Zener voltage, and we limit the current through it by a resistor. So once you have this sort of thing here, this voltage here will remain very constant, providing that you do not ask the Zener diode to handle more current than it can. So again, for very low sort of power supply, low current power supply applications, you can put a Zener diode in parallel with the unfiltered, sorry, the unregulated power supply, and you can get a nice regulated supply, but low current, all right? And these are all things about the characteristics of where the Zener is and so on. And if you ask the Zener to supply more current than it can, then the Zener will, of course, fail and it's down. And these were some calculations relating to how we can design that particular type of device. So it's all there. You could go through that. We did that in class, right? They're useful for low power regulations, regulation and so on. But usually not more, and there's some little, the diode, remember the Zener diode also has a resistance in it, so the regulation is not the best. So what can we do to improve that? Well, the next way to do it is to find a way to let the Zener diode provide a constant voltage to some other device that can handle the current that we really want. And this is where now we go on to the next level, where we put a transistor here. So we have the basic Zener diode here, but instead of taking the voltage, the useful voltage at this point, we pass it through a transistor now. And what we do is that we ask the Zener diode now to supply a constant voltage at the base of the transistor here. And if you remember, again from the circuit theory, so this will be VZ, so that the output here is going to be VZ plus 0.7 volts, right? Because we have to sorry, sorry, my mistake. Here, right? We need 0.7 volts to bias the transistor on. So here, right? If here is at VZ, then here is going to be at VZ minus 0.7 volts. Or if you want V out here, then here is going to be V out plus 0.7 volts, which is VZ. Either way you can look at it, all right? So once you do that now, what happens is that the current being asked from the Zener is limited to the base current of the transistor. And remember, the base current of the transistor is whatever is you're asking the transistor to supply. So if the transistor has to supply a load current of IL, its base current is IL over HFE, right? And if it's a moderately heavy transistor and HFE is, let's say, 50, right? Then the Zener is being asked to supply 1/50th of the load current, which is a lot smaller than if you didn't have the transistor in its way. And so the Zener now just is simply acting as a voltage reference, right? Right, and this was the calculation here, right? And some examples here, and we actually went through the process. Okay, and some of the things we spoke about, of course, had to do with the fact that that the Zeners themselves, first off, the Zener, these things only come in certain voltages. You can't get any and every voltage that you want. So sometimes you have to be careful. So if you want a 12-volt supply, like in this case, we took a 13-volt Zener. So by the time you took away the 0.7 volts from it, you have 12.3 at the output here. If you were to use if you say, I want 12 volts here, and I get a 12-volt Zener, then in fact, I'm not going to get 12 volts, I'm going to get 11.3 instead. All right? So there were some little issues inside of here. And then we had some questions inside of here. First off, the regulation is better because you're asking the transistor is taking the load instead of the Zener. Notice that the transistor, let's see what this question was asking. This question, right, the transistor is 100 milliamp load, so the transistor is actually being asked to dissipate nearly a watt, okay? So so this transistor here, you have to pick a device that could handle at least 1 watt, okay, without burning up and things like that. So you can, when you look back the notes and review the original recording if you have to, right? So what happens again, and another thing, what happens if the transistor shorts? So to improve it, we added one more component inside of here, which was, we had this shunt component here. This is a shunt regulator. This is the series part of it. And now what we've done now is to put in inside of here now another component in here, which we're going to call an error amplifier. And that now is going to try to give us even more control over the type of voltage that we're dealing with. Yeah? Right, if any of this thing, if you want clarification, of course, for anything here, please let me know, right? Right, so we had this here, right? And then, oops, let me stop sharing this one here. I wanted to share this one. Wait a minute, just have to exit this one. Hold on. Good. Share this one instead. Nice. Right? So, hey, what am I doing? I think I'm sharing the wrong. Which one is this? This is 2A. Yeah, sorry, I'm supposed to be sharing 2B. Keep sharing the same thing. Lecture 2B. Where's 2B? There we go. This is the one. Right. So we spent now, so we did this, we went through here. Right, and we're now introducing this error amplifier here. And the first approach to making the error amplifier was to put an additional transistor in place here. So we put this transistor TR2 now into the circuit. All right, so we add this. Where's my pointer? Okay, just a second. I realize what I'm doing here. I'm sharing a PDF, not the. All right, just give me a second. Okay. Right, so back here, share. I had too many things open up. Going to share this one. Good. Now we go. Right. So we put in. No, wait a minute. Okay, yeah, we doesn't. Let me stop this one here. I'm getting myself confused here. I'm supposed to be sharing. Where am I? Power supply A, B, this one. Right. So we took the element there and we've now added a transistor into it. And the transistor now, notice what is happening, that the Zener diode now, instead of providing the reference voltage to TR1, is now providing a reference voltage here to the emitter of this transistor. So if that is the case, and look what happens here now, this is my output. So I'm creating a reference voltage from the output, or feedback voltage, I should say, from the output, which is whatever the output voltage that I'm designing for, and it's divided by this voltage divider, right? So I have V feedback here, and I have VREF at this point in time. So what I'm actually controlling is the collector voltage at the output of TR2, which incidentally is a base voltage for TR1. All right. So we have the designations here. These are all in the slide already, right? Which is what I'd given you. That's why I don't want to mark over what I have there already. And how it operates is that if for some reason the output voltage goes up, then the reference voltage here, or the feedback voltage here, is going to change. And if this changes, in other words, if the base voltage of the TR2 increases, it's going to cause TR2 to conduct more. If TR2 conducts more, it pulls more current through this resistor and drops the collector voltage. And if the collector voltage drops here, it means that the base voltage for TR1 will drop and the voltage output will drop. Right? So as if this increases, the TR2 tries to bring it down. And if this decreases, all right, then TR2 stops conducting and it reduces the amount of current through this resistor R3. So VCTR2 starts to go back up. Okay, so that's how the regulation works. right? And we have the slides gave us the calculations and gave us how to do the various calculations. It's all somebody had asked before. It's all simple circuit theory you're dealing with, right? The Zener diode voltages, current through resistors. This is a bias, a simple voltage divider here. And to know some properties of the transistors, the bias, the relationship between the HFE and ID and IE, okay? And then after that, the rest is fairly straightforward. So where that led to is that, okay, you could use a transistor, but then when you're talking about errors, then one of the, an op-amp is ideal for this kind of thing, where you put a reference voltage on one terminal and you have a control voltage on the other or a feedback voltage on the other. And that's where we come up with this particular configuration, or which is getting to the exam question, right? And I'll share that one now. So that takes us to this particular one here, right? So that if we replace the op-amp now, and we're almost there, so what we've done, instead of having the transistor here, right, with this, the resistor and so on feeding it, and the Zener here, what we've done is that we replace this transistor, the transistor circuit itself, we've gone and replaced that now with the op-amp, right? So how does this work? Again, back to simple op-amp behavior. If I take my Zener reference now, so remember here is at VZ, okay? Because here is at VZ, and because of the op-amp behavior, it tries to make here VZ as well, right? Because of the open loop gain, the high open loop gain of the op-amp. If you put VZ on the inverting terminal, on the non-inverting terminal, it is going to try to make the inverting terminal equal to VZ internally. So if you put VZ here, the op-amp tries to make VZ available at this point. So if VZ is available at this point, okay, then the output voltage V out, if VZ is here, then the current through this is VZ over R2. And therefore, that current, remember the current into the op-amp is very small. So that current essentially is passing through R1 and R2, which means that V out is VZ over R2 multiplied by R1 plus R2, which gives you this particular here, right? So the output voltage now, you could calculate, once you know VZ, you could determine the value of R1 and R2 to give you nearly any output voltage that you need, right? What happens is that if the voltage here fluctuates, because if the voltage here is fluctuating, either up or down, here is clamped at VZ. So when the voltage fluctuates up and down, because you have clamped here at VZ, this is fixed. That current is essentially fixed so that the transistor, the op-amp keeps driving the current here to keep that from varying. And it's almost immune because of the fact that I've put VZ here, the transistor, the op-amp will send current through the transistor, which will send current to ensure that VZ maintains, sorry, at that point maintains the voltage at VZ all the time, right? So that's all part of the open loop behavior of the op-amp inside of there, all right? And then, of course, we made some changes about where we can bias the op-amp from. That here I'm biasing it from the unregulated supply, and the Zener is also supplied here and so on. And there were variations of that we could have done. We could supply one from the regulated and one from the unregulated and so on. Okay. and there was a design calculation inside of here, right? And then this particular version now is that the Zener is supplied from the regulated supply, but the op-amp is still supplied from the unregulated. Anybody remember why? Right? Why did we supply the op-amp from the unregulated supply and not the regulated supply? Anybody recall?
No, sir.
All right, it has to do with this voltage here. All right, remember we need a positive 0.7 volts here. In other words, the output of the op-amp has to be bigger than V out. Okay, by at least 0.7 volts. If I'm supplying the op-amp from here, right, which is V out, remember the op-amp, an ideal op-amp, if you're supplying it from V out, the V out SAT for the output of the op-amp is typically about 1 volt less than VCC. So if I'm supplying the op-amp from the V out terminal, it means that the maximum voltage that I can get here is going to be about 1 volt less than V out. That can happen. I need a voltage here to be greater than V out plus 0. By at least 0.7 volts. So in other words, if I were to supply it from the regulated side, the op-amp will not be able to provide enough voltage here to keep the output voltage at the design level, right? So you have to have a bigger supply voltage for the op-amp, so you could take it from the unregulated side. It doesn't apply to the Zener because the Zener voltage here is typically about half V out. You pick a Zener that is fairly close to about half V out. So if you're designing a 20 volt supply, VZ is typically about 10 volts. Right, so you could supply that easily from here. It's unregulated, so you could get a nice clean current supply coming to the Zener, so that the voltage here at this point here at the terminal for the non-inverting terminal for the op-amp is nice and steady at 10 volts. All right, fair enough. Yeah.
Yeah.
Okay, so this now takes us to what the question was, right? We now in the position to answer. Here we have the op-amp regulator. The only difference now between what we just did and what is here is that we've put a Darlington pair instead of the regular pass transistor. So the question is asking us now, everything that is based there, design voltage regulator to supply 19 volts at 1.25 amps. That is going to supply a half wave, is going to be supplied from a half wave rectifier, a 21 volt transformer. The ripple is 2.5 volts peak to peak. And both transistors have HFE equal to 50, right? So when you're designing it, so what you have to do to design it, you go back here and you're going to have to, right? So you have to specify some parts inside of here. So if I were to just, let me just change color here. So this is 19 volts here. This is, you're coming here from an unregulated a 21 volt transformer, right? So if the transformer here is 21 volts, right? Then what is the maximum voltage coming off of the transformer? V max unregulated is going to be 21√2, whatever that is. I think that's about 29 point something volts, 29 point something, 7 or 8, something around there, right? For this thing, we have to, if you look here, we're going to have to choose a value for D. We're going to have to choose a value for R3, choose a value for R1, choose a value for R2. On the other side, they told you a half-wave rectifier, right? So, and they give you the ripple, V ripple is equal to, I think it's 2.5 volts, right? So we have to calculate the reservoir capacitor value inside of there, right? If we assume 60 hertz and the ripple is 2.5 volts and the capacitor is the maximum current, which is 1.25 is I over delta V, which is 2.5 by 60 hertz, and you get something like a very odd number, 833 microfarads. And remember me telling you that you're not going to get these things just so, right? You get something like 5,000 microfarads, right? So what to get this, you also get values like 2,200 microfarads, 1,000 microfarads. You get these kind of values. You may even get 10,000 microfarads, which is a big fella, right? So what you would do is that you look at this, and if this is what the calculation is telling you, then you probably want to go a little bit bigger than that with the available units that you have. So I would probably put two 5,000s in parallel. The good thing about capacitors is that when capacitors in parallel, the values add, right? So for here, instead of C, you could put well, the calculated values for the exam, this is for the exam. So it would give me this, and this is the answer here. But in practice, you would probably put a 5,000 in parallel with another 5,000, right? Something like that. Or if you don't want to use, because these things are expensive, okay? What you would want to do maybe to reduce the capacitor value here, in reality, don't use a half-wave rectifier, use a full wave, okay? Then on as you go across to here now, so we need to calculate the three resistances on one diode. If the output here is 19 volts, typically we want the Zener diode VZ to be approximately half V out. So V out is 19, half of that, you're dealing with 9.5. So you could probably pick a 9 volt Zener or 10 volt Zener. Your choice. If you're whatever you're done in the exam, I would work backwards for that, right? I would probably wouldn't go as low as 8, but you could get away with 11 on that side. You want to stick kind of close to the halfway mark for the Zener. So once you know the Zener, value here, so if the Zener, if you pick a Zener, let's say a 10 volt Zener, right? Typically, the Zeners need 5 to 10 milliamps for the, what do you call it, to current. So if this is 10 volts here, and this is 19 volts here, right? And you need 5, let's say 10 milliamps passing to bias the Zener, then you could calculate R3 at that point in time, right? So it'll be 19 minus 10 divided by the 10 milliamps, and that will give you the value for R3. What about R1 and R2? So if you pick 10 volts, here is going to be 10 volts. Okay? What is the current through R2? The current through R2 is going to be 10 over R2, and the voltage coming out here is R1 plus R2 over R2, right? And that is equal to 19 volts. So this now is going to give you a relationship. R1 is equal to some factor of R2. Okay, so what you do, you pick R1 or you pick R2. So you could pick R2 equal to, let's say, 10K. So R1 will be K times that. Or you pick R1 to be 10K and R2 is 10 divided by K. All right, and that's your solution there. Yeah, questions? You all right?
So far, yeah.
Right, very straightforward, very, very easy. There are other part of the thing, but the same thing. What was the maximum, the base, and then this one always asks you the base current of the various the points. So once you design it now, what is the base current? If this is going at 1.25 amps, then the base current here is 1.25 divided by 50, which is the HFE for this. And then the base current here is that current now divided by a further 50. Okay, so you could work out whatever it is. This, I think the solution that this is 25 milliamps. So the current here is going to be 25 milliamps over another 50. And that's what the op-amp has to provide, which is very small. Okay.
So for the voltage at the output of the op-amp, why did they add 0.7 twice to the 19 volts?
Why? Because what happens is that, look at this. For this transistor to conduct, here has to be 0.7 volts. This point has to be 0.7 volts higher than 19. And for TR1 to conduct, here has to be 0.7 volts higher than there. So in other words, this voltage here has to be 19 volts plus twice 0.7. Yeah?
So since you're dealing with two transistors, you're adding these 0.7 twice.
Correct. Right? It is two transistors. The Darlington pair are two transistors, so that they sort of overall, if you were to call this big C, big B, and big E, the VBE for the Darlington is approximately 1.4 volts, right? You have 2.7s to deal with here, right? Yeah?
Yeah.
You sure?
Yeah, for now.
Okay, all right. All right. And then the last part of the question asks how to introduce short circuit protection into this. And that short circuit protection now was the last part of the discussion that we had on power supplies, which was this one here, right? Which we spoke about, right? So you make a power supply now, but what happens if you short circuit? If somebody, or it happens in the lab, you're making something or you're using it, or accidentally the wires from the power supply touch each other. What happens? Well, in a situation like this, if the power supply touches each other, you're going to short, you're going to ask the transistor basically to supply current into a short circuit. All right? So what you want to do now is to avoid overloading or shorting out the transistor. And what we do is that we can put another transistor in the circuit here. So what this has done is that you put a small resistor here, and notice you have a transistor here. Notice the configuration of the transistor. So if this transistor, as the load current passes through R4, the voltage across R4 is going to rise. Notice this voltage is the turning on the bias voltage for this new transistor inside of here. So as soon as this voltage across R4 gets to greater than 0.7 volts, this transistor starts to turn on. And once that transistor turns on, it is going to take current this way. If it takes current that way, then, and of course, once this turns on, now when it starts to pull current drive away from this transistor now, this transistor starts to turn off. All right. So the more current, once this transistor is turning on, as soon as this rises to above 0.7 volts, this transistor turns on now and starts pulling away current from the base of TR1. And because this voltage is now clamped at 0.7, right? The transistor here is now not going to be able to supply any current more than it is, because even at short circuit, if you supply this into a short circuit, R4 is going to limit the current in such a way that the voltage here is always 0.7 volts. So it's not going to let it supply any more current than whatever you design R4 to be. So in other words, now the current, this transistor, when you start a short circuit, the device now, the voltage drops, but the current starts to get constant. So in other words, you enter a constant current mode. The voltage is going to drop because as you drop the current drive through this, right? The transistor starts to turn off so that the voltage starts to go down. Right, so you enter a constant current mode at that point in time, right, which is all explained here. And the more you eventually, if you can't take any more load, then the current drive, as you keep cranking it up here, the current drive to this TR1 is eventually going to shut down to zero, and the output now will fall to zero. Okay. So the characteristic looks like this. So the output is here, and your current increasing slowly. So you have a increasing voltage and current going here. At some point in time, because of resistor R4, TR3 kicks in and the output voltage starts to drop, but the TR3 is limiting the current constantly now through R4, but the output voltage is dropping, and eventually the thing shuts itself down if you ask it to provide more than IC max. All right. At maximum current, the pass transistor, remember the pass transistor now is handling the maximum power. So if you look at it at shutdown, when this thing shuts down, here essentially 0 volts. Here is whatever V unregulated is. So like in our design, if V unregulated is something like 29 volts and V out is 0, and you have 1.25 amps that it is limited to, the transistor is going to be asking to calculate 29 by 1.25 amps, right? Which is about 40 watts. So this guy is going to get very hot, which is why it has to be mounted on things like a heat sink and so on. If it is not, then it's going to burn out, all right? And the other version, which we spoke about when we were talking about the other past paper, is a variation to the circuit. So instead of asking the transistor here to start carrying all of the current, as it shuts off, what we want to do now is to fall back, is to try to reduce the voltage here, so that at this point, if we reduce the voltage in the fallback as well, then what happens is that the current, the power being dissipated by the transistor is going to reduce. All right. So to do that now, we add 2 other resistors to the same pass transistor. And the explanation is all here. So at this point, what happens is that as V out, there's the usual voltage drop, TR3 starts to turn on, but there's another couple of resistors, R5 and 6, that change the bias point at Vx. Right, so as the voltage drops, V out drops, so that the the current being asked to pass is going to be a little bit less, and you keep dropping the voltage down less and less. Okay, and the calculations are all here. So as IL increases, VO drops, but VX also drops as well. So you kind of gently lower the whole voltage for it, and the pass transistor will carry it asks it to carry less current because it's dropping the whole protection circuit, is actually dropping the entire regulation voltage out to below. So instead of following this line here, it reduces the current through the transistor as well. All right, so that it handles a little bit less current than before. And the calculations are all there. All right. And the process, of course, and this was the exam question, you typically, given this, you have to choose R4. R4 is usually small, right? Like less than 1 ohm. Then you calculate rho. Remember, rho is the relationship between 5 and 6. All right, and some voltages. Sorry, rho is the relationship between the output voltage and the output voltage and the voltage across R4. Okay, so once you do that, in fact, you don't need to remember rho. We could calculate it from straight circuit theory. You know that if I have V out here and I have a current flowing through here, that V out bar is equal to IL R4, right? What do you call it? Sorry. The current through R4 is V out, V out bar minus V out. That's it. That's the voltage across R4. So the current through R4 is this, right? So that is IL. All right. So that at that point, once you know that, and then if you know V out, you know that Vx is equal to V out bar over R6 plus R5 multiplied by R6. So you have everything inside of here. You know this because you determine that. You choose a value for either R4, R5, or sorry, R5 or R6, and then you calculate the other one. So you have everything here, and you pick this. You pick R4 as well. So you pick R4, and then you choose a value, R6 or R5, and then you calculate the other one. All right. In the case of the particular question being asked, the only difference in our question here is that we now have an op-amp. So the protection circuit, let me just clear some of the garbage here a little bit. All right, and then share the screen and go back to where's the okay, so if you go back here now, the only difference here is that you're going to put the pass transistor between here, right? Remember what the configuration is. The pass transistor now has to attach to the base here, right? And the collector of the pass transistor, let me just note there, I've drawn this very bad. Put in the pass transistor, let me just pick a different color here so it looks a little bit clearer. I'm going to put in my pass transistor here. So this is the transistor, right? The transistor comes here, right? We're turning on the transistor here, and the transistor is going to attach right here. So as soon as R4, as soon as this turns on this transistor, it is going to pull current through here that will reduce the bias for TR1 and therefore the bias for TR2 and slowly shut the thing down. Okay? And it's as simple as that. So questions, we've gone past 11. I missed it.
So I have two questions about that.
Mhm.
The first one is, if they ask us for the overprotection circuit, which one do we draw? This one that you just, well, I see you show us. This one, and then one with a potential divider incorporated.
Okay,
Which
so
one?
one is overcurrent protection and the other one is fallback protection. So if I just, so if the question just asks for how electronic short circuit, use the simplest one, which is this one, right? If I specifically ask for fallback protection, that's the other one, which is what I asked for in the December paper, right?
Oh.
Mhm.
And,
And the other question.
if they give you the diagram and they ask you to draw it, are we expected to just draw the additional components or redraw the whole diagram with it?
In this particular case, it might be easier to draw the entire diagram and show where you're fitting in that component. It's a little hard I mean, if you given the Darlington here, right? So you're coming, right? So you put that here. I mean, you could technically do this for me. So what am I doing? Do this and send that back and draw it like this and just tell me that this is how the additional component would work, right? Of course, label it TR2, TR1. This is now TR3, 4, and indicate to me that this is the protection circuit. Of course, you could say to op-amp, for instance. That would be acceptable if you do it neatly, okay? Just to show me how to insert it.
Yes, sir, thanks.
Okay, but do everything neat and label it for me properly. Draw
Yes, sir.
whatever you're taking from the main circuit, do it exactly as they have it. All right. Right, so any other questions?
Sir,
Yeah,
can you hear me?
yeah, perfect.
Could I speak to you afterwards?
Yeah, not a problem. Right, so once we finish here, I'll so any other questions related to the course? Okay, so if not, I'll stop here.